Welcome. In this scene, we'll explore a powerful technique in calculus called integration by substitution. Substitution helps us simplify complex integrals by introducing a new variable. Think of it as changing your perspective to solve a tricky puzzle. Let's consider this integral, the integral of 2x times the square root of x squared plus 1. At first glance, it's not immediately clear how to integrate this expression. Here's where substitution comes in. We can define a new variable, u, to represent x squared plus 1. This substitution allows us to rewrite the integral in terms of u, simplifying the problem. The key idea here is that substitution transforms the integral into a form that's easier to handle. By focusing on this new variable, we can proceed with the integration process more efficiently. Substitution basics. In this scene, we'll explore how integration by substitution works and see how it simplifies complex integrals. Let's start with this integral, the integral of 2x times the square root of x squared plus 1. At first glance, it might look a bit intimidating, but substitution can make it much simpler. The first step is to identify a substitution. Notice the term x squared plus 1 inside the square root. We'll let u equals x squared plus 1. Next, we compute the derivative of u with respect to x. Since u equals x squared plus 1, its derivative is du equals 2x dx. Notice how this matches the 2x dx term in the original integral. Now, we can rewrite the integral in terms of u. Substituting u equals x squared plus 1 and du equals 2x dx, the integral becomes the integral of square root of u du. What was once complex is now much simpler. This is the power of substitution, transforming a complicated integral into a more manageable one. Here, the integral is now expressed entirely in terms of u, ready for further simplification or evaluation. Now that we've substituted and rewritten the integral in terms of u, let's solve it step by step. First, we'll rewrite the square root of u as u raised to the power of 1/2. This makes it easier to apply the power rule. The power rule for integration states that when you integrate u to the n, you add 1 to the exponent and divide by the new exponent. Applying this here, we get u to the power of 3/2 divided by 3/2 plus the constant of integration plus c. Next, we simplify the fraction. Dividing by 3/2 is the same as multiplying by 2/3, so the result becomes 2/3 times u to the power of 3/2 plus c. And there we have it. Our final result for the integral in terms of u is 2/3 u to the power of 3/2 plus c. In the next part, we'll substitute back in terms of the original variable to complete the solution. At the top of the screen, we see the result from the previous step. Integral u2 du equals u3 over 3 plus c. This is the integral expressed in terms of u. But remember, we made a substitution earlier. U equals x squared plus 1. We'll need to use this substitution to rewrite the result in terms of x. Starting with u cubed over 3 plus c, we substitute u equals x squared plus 1 into the equation. Watch carefully as we replace u with x squared plus 1. After substituting and simplifying, we get this final expression, x squared plus 1 cubed over 3 plus c. And here it is, the final answer in terms of x, boxed and ready. Now, let's apply substitution to a more complex integral. \int x cos x2 dx . This example will help solidify our understanding of the substitution process step by step. The first step in substitution is to identify a part of the integral that we can replace with a new variable, \u . In this case, we'll set u equals x2 . This choice simplifies the argument of the cosine function, making the integral easier to solve. Next, we compute the differential \du by taking the derivative of u with respect to x . Since u equals x2 we find that du equals 2x dx . Notice how this derivative relates to the x dx term in our original integral. We can now rewrite the integral in terms of u . Substituting u equals x2 \, and do equals 2x backslash dx backslash, the integral becomes backslash frac12 backslash int backslash cos u backslash do backslash. This transformation reduces the complexity of the integral. The rewritten integral backslash frac12 backslash int backslash cos u backslash do backslash is straightforward to solve. The integral of backslash cos u backslash is backslash sin u backslash, so we get backslash frac12 backslash sin u plus c backslash. Finally, we back substitute backslash u equals x2 backslash to return to the original variable. This gives us the solution backslash frac12 backslash sin x2 plus c backslash. And with that, we've completed the substitution process. Now that we've explored the details of integration by substitution, let's recap the key insights you'll need to apply this technique effectively. The process of integration by substitution can be broken down into 5 clear steps. Let's go through them one by one. To excel at substitution, keep these practical tips in mind. Of these tips, 2 stand out as especially important. First, always choose u wisely. This decision simplifies the entire process. Second, never forget to back substitute. This ensures your solution answers the original question. In this final segment, we'll solve one more example of integration by substitution to solidify your understanding. Here, we have the integral of sine of 2x times cosine of 2x with respect to x. Let's solve this step by step. First, we'll make a substitution. Let u equal 2x. Then, the derivative of u with respect to x is 2, which means do is equal to 2 dx. Rewriting the integral in terms of u, we have sine of u times cosine of u divided by 2. Now we simplify. The coefficient 1/2 comes out of the integral. Recall the trigonometric identity. Sine of u times cosine of u equals 1/2 sine of 2u. Substituting this in simplifies the integral further. We're now left with 1/4 times the integral of sine of 2u with respect to u. The antiderivative of sine of 2u is negative 1/2 cosine of 2u. Now, we back substitute u as 2x. This returns us to the original variable. Simplifying further, we arrive at the final solution, negative 1/8 cosine of 4x plus c. And that's our final answer. Great work following along.